What happens to a physical object if you completely delete its distance, shatter its angles, and erase its size? Common sense says nothing is left, but common sense is wrong. What remains is a pure, indestructible skeleton. Welcome to Stayblocks. Today, we are taking a deep dive into the bare foundations of space itself. The framework we are exploring is defined in the study of incidence geometry. In this system, measurement does not exist. The only data point available is a pure binary relationship. Does a point lie on a line, or does it not? Yes or no, 1 or 0. For thousands of years, classical geometry relied on physical tools, rulers to verify length and compasses to lock in angles. Shapes were defined by their tangible constraints. Stripping away these human constructs of scale reveals the absolute connectivity of spatial reality. We stop looking at the skin of geometry and start looking at the bones. Wait, let's look closer. How do you navigate a space where physical rulers do not exist? A physical city map dissolves into a subway network. When you ride a train, the exact physical mileage between station A and station B is irrelevant. The only truth is whether a route directly connects your stops. When a station sits directly on a route, a point on a line, they form a flag. If a point exists independent of a line, the pair is an anti-flag. This establishes the baseline for partial linear spaces. In these systems, the rule is strict. 2 distinct points determine at most one connecting line. Defining space as a network of flags and anti-flags allows data scientists to map non-physical realities, like the internet or complex social networks, where mileage has no meaning. Now, here is the part that keeps physicists awake at night. If we have thrown away the ruler, how do we measure the gap between 2 disconnected points? We use a bipartite tool called the Levy graph, or the incidence graph. A bipartite system in action splits the universe in half. Points are nodes in a vertical column on the left, and lines are nodes on the right. Crossing edges are drawn between them only when an incidence exists. Distance is redefined as a count of the shortest network steps required to travel from a point node, through a line node, and to your destination point. By ensuring that points can only link to lines, the Levy graph enforces a rigid hierarchy. This prevents the combinatorial ambiguity that occurs when connections are allowed to form at random. Converting physical geometry into bipartite network steps creates a universal language measuring environments that have no physical dimensions. This brings us to the celebrities of incidence geometry, shapes that obey these combinatorial rules but challenge our physical intuition. Meet the phanoplane. This maps the construction of an order 2 projective plane. It contains exactly 7 points and 7 lines, including the central circular path functioning mathematically as a straight line. Every single line in this shape contains exactly 3 points. It lacks an ordinary line, a line containing only 2 points. Because it lacks a 2-point line, the phanoplane cannot be drawn using strictly straight lines on a flat piece of paper. It is a logical certainty that is physically unrepresentable in our 3-dimensional reality. Wait, let's look at another anomaly, the Hess configuration, an order 3 affine plane. The Hess configuration features 12 lines partitioned into mutually disjoint parallel classes. In these sets, the lines never share a common point. If you remember our previous look at projective geometry, you'll know how parallel lines behave here. But incidence geometry shows us the structural skeleton that makes those rules possible. The phanoplane and the Hesse configuration demonstrate that perfectly logical mathematical spaces exist independently of human physical limitations. Even in an abstract void, total chaos is impossible. Strict combinatorial laws govern the arrangement of points and lines. We see this in the Sylvester-Galai theorem. This diagram shows the rule. In any finite set of points, unless every single point is aligned on a single track, there must exist at least one line that contains exactly 2 points. This theorem is the reason the phanoplane cannot be physically realized. Because the phanoplane requires 3 points on every line, it violates the connectivity laws of our physical plane. There is also a rule of absolute minimums, known as the de Bruijn-Erdős theorem. This theorem mandates that a set of n non-collinear points in a projective plane will always force the creation of at least n distinct lines. 10 points will always guarantee at least 10 connections. These theorems act as the underlying logic for non-physical spaces, ensuring that structure always emerges from nothingness. Theoretical bounds reach their limit with the Semerady-Trotter and Beck's theorem. Beck's theorem dictates two extremes for any collection of points. Either a massive fraction must align on a single line, or a dense web of lines is required to connect them. These extremes are governed by the upper bounds established in the Semerady-Trotter equation. Removing the ruler and the compass leaves us with the raw architecture of connection. This skeleton of flags and anti-flags provides the core logical foundation for any space, whether physical or digital. Understanding these incident structures simplifies the complex networks of our world. Join us for more mathematical deep dives by subscribing to StyBlocks at youtube.com/StyBlocks and join our community of thinkers.